Okay, so welcome back. Today we're continuing our lectures on probability, and we're going to get into the topic of conditional probability. And so mostly that's just a definition, but it's important that we understand that definition and that when we get confused or we're unsure about something, that we refer back to it. Nice thing about today's lecture is there's a couple of surprises or counterintuitive results. So here's one of them. This is called the Monty Hall problem or the Monty Hall dilemma. It goes back to a game show from the probably 70s in which at some point in the game the contestant is faced with the following situation. There's 3 doors. You don't know what's behind them, but you do know that 2 of those doors have a goat behind them, and the third one has a brand new sports car. You would like the brand new sports car. So the game's played like this. You choose a door, and either you choose it at random or the organizers of the game show have randomly assigned the cars and the goats to doors. It doesn't really matter. So let's say you choose at random. So you choose this door. Let's say that's your random choice. Now the host of the show, Monty Hall, he knows what's behind everything. He knows what's going on here. He knows where the car is and where the goats are. He opens one of these 2 doors, and when he opens it, so what you see back here is a goat. He always opens a door with a goat behind it. Okay. And now he says, well, would you like to take what's behind the door you chose, or take what's behind the door you didn't choose that I haven't opened yet? So the question is, what should you do? And also, for us, well, for whatever you decide to do, what's the probability that you win if you do one choice or the other? Yep.
The door is already open.
Pardon me?
One door is already open. Isn't it 1 out of 2?
Well, it depends what you want to do. So your next step could be to toss a coin and pick one of these 2 doors at random. And then you know one of them has a goat behind it and the other one has a car behind it. And if your coin comes up the right way, you'll win. So you can win with probability 1/2 if you toss a coin next to decide. Can you do better than that? So switch all the time, no matter what?
Yeah, I think so.
Okay. So up until this point, basically the game plays out the same regardless, right? So there's nothing really weird that can happen. So one strategy is always switch to the other door, and another strategy is stick with the first door. And then there's the third strategy of tossing a coin to decide. So tossing a coin to decide, we know what's going to happen. So strategy 1, toss a coin. And in that case, the probability of winning is 1/2. Strategy 2. Stick with your first choice. So if I stick with my first choice, what's my probability of winning? Well, let's think about it. I picked a door at random, one of the three doors. Exactly one of the three doors has the car behind it. And no matter what happens next, I'm going to open that door. So really, I'll only win if my choice was the one with the car behind it. And the chances of that happening is 1 out of 3, right? So in that case, the probability of winning is 1 out of 3. And strategy 3 always take the other door. So let's think about the way, rather than the ways I can win at strategy 3, let's use the complementary rule and see how I could lose. So I pick this door, Monty shows me this door, and then I open this one. What does that mean? Where's the car? Yeah? Yeah, it means that the car is behind the one, the door that I chose first. That was a random door. So strategy 3 can only lose if strategy 2 wins. Right? So pick a random door and open it. That has probability 1/3 of winning. Pick a random door, wait for the host to open the other door, and then take the unopened one. That has probability 2/3 of winning. And the reason is that because we only lose if our first guess was correct. And that first guess was completely random out of 3 choices. So this one, many of you have probably seen before, but it's certainly worth it's worth knowing this result, and it's an interesting thing, and it's a place where our intuition guides us wrong. 2/3 seems way too good, right? I mean, it didn't seem like you should be able to do that well. The sort of 50-50 one is the sort of the obvious one, and that's where most people would think, well, there's still 2 choices left, and there's only a goat behind one of them, so you can only win with probability 1/2, but actually you can win with probability 2/3. All right. So, questions about that? Everyone believes that? Okay. So this is the best strategy. There's nothing you can do that will give you a better chance of winning than that. Okay. There's another puzzler like that. So first of all, when we talk about people and their children, we'll assume that the sex of the child is uniformly random, meaning, and it's binary, so the child is either a boy or a girl. That's just the model we're using. So here's what I'm going to tell you. Anil has 2 children. At least one of them is a boy. What is the probability? Okay, so there's 2 ways to say this, but I'll say that the other one is also a boy. Okay? So who wants to guess? So we draw the probability space, or we figure out what the probability space is. Well, there's 2 children. First one can be a boy, the second one can be a boy. There's first one can be a girl, second one can be a boy. They can both be girls, or it can be a boy and a girl. 2 boys, first a girl, then a boy, 2 girls, or first a boy, then a girl. Yeah. Yeah, so I'm saying at least one of them is a boy, but without knowing anything first, when I say he has 2 children, that's what the space looks like. Okay? And with our assumptions about everything being uniform, what we have is that the probability of omega is a 1 over 4 for any omega in S. So each of these is equally likely 1 over 4. Okay? Now, I tell you that at least one of them is a boy. So that means actually all of these are not possible. Only these 3 are possible. In how many of those, so each of those 3 is equally likely, in how many of them do Anil has 2 boys, knowing that at least one of his children is a boy? The answer is 1/3. Kind of surprising, right? Binary problem. And we end up with a 1/3 in there. I mean, a lot of people would think at the beginning, okay, well, the gender or the sex of one child does not affect the sex of the other child, but that's not really what the question is saying. The question is saying at least one of them is a boy. That restricts the list of possibilities. They're still all equally likely. And in this case, there's only 3 of them, and only one of them has them both being boys. Yeah.
Why is GB different from BC?
Because they have 2 children. One of them was born first, and the other one was born second. So it could be that the first one was a girl, and the second one was a boy, or it could be that the first one was a boy, and the second one was a girl. No, it didn't specify. It just said that at least one of them is a boy. So of the 4 possible sexes of those 2 children, there's 3 of those where at least one is a boy. That's all the second condition says. Okay. So I'm going to write that here, and I think I'll write it over here just to save it for later. Probability that Anil has 2 boys, given that Anil has at least one boy is equal to 1/3. Now, let's try and make this as rigorous as possible. And for that, we'll start with a definition. Which is the following. So definition, A and B are two, let's say, events in some probability space. Remember, a probability space has the set of possible outcomes and the probability function that maps those outcomes onto probabilities. So A and B are two events, and such that there's a little condition required that the probability of B is bigger than 0. Then here's the definition. The probability of A, and this vertical bar here, you read it as the word given. So the probability of A given B, that's just the probability of A and B divided by the probability of B. Okay. So this is just the definition. Let's try and understand what it's telling us, or what it's supposed to capture. So we have this big set of possible outcomes here, S, and we have a set A, and we have a set B. So anytime you run this experiment, you land somewhere in this universe. So what this is supposed to capture is what happens if I restrict myself to runs of this experiment where I get something in B. So really, I run this experiment, I get an element from the set S, and if it's not in B, then I run the experiment again until eventually I get something that's in B. And what is this thing measuring? Well, it's got the probability of A intersect B on top here. So that's this area, right? This is the A intersect B, and then divides by the probability of B. And so if you think about this for a little bit, well, what's really happened is, just imagine that I kind of change the experiment now so that the only thing that can happen is something in B. And sometimes that stuff that's also in A happens. And so this is really saying, or we interpret this as, if I tell you that B happened, what is the probability that A happened knowing that? Okay. Right, so we imagine the dividing by B here is because, essentially that, remember, probabilities are supposed to sum up to 1, but if I sum up all the things in B, they don't sum up to 1, they just sum up to the probability of B, and so I divide by B so that the probability of B so that they sum up to 1. So it's just like we do this experiment, and actually we keep trying it until the first time that we get a result in B, and then we can ask questions about, well, what's the probability of A in that first try. And it's really, how much of B does A take up? And that's A intersect B, and if you take it as a fraction or as something, a fraction of 1, then you have to divide by probability. So let's try and use that over here. So in this question about Anil's children, there's our set S. Our set B, where we said Anil has at least one boy, that restricts it down to this set. And our set A, which is what's the question, does Anil have two boys? That's this set. And so we can apply the definition. Probability of A given B is equal to the probability of A and B divided by the probability of B. A intersect B, well, there's only one element in common between those two things. So that's just the probability of two boys. That's what's on top. And B is this set. So that's the probability of B, GB, BG. Now the probability of BB is 1 out of 4 because it's a uniform probability space. And the probability of this one, there's 3 elements. Each one has probability 1 out of 4. So that's 3 out of 4, which is 1/3. So that condition, Anil has at least one boy in this probability space, that corresponds to this condition B here, or this event B. So yeah, we call this the conditional probability of A given B. We call B, even though it's an event, which is just a set, we sometimes call it a condition, because just to match the way we use sort of natural language. Okay. And this is a really useful notion, and we'll see, we'll work through a few examples now, make sure that it really behaves the way we expect it to behave. And then we'll look at least one example where it does something really surprising. Okay. But now is the time to stop me if you have any questions. Okay. Good. So let's leave that definition up for a while. So here's an experiment. We roll a 6-sided die, one of our favorite classics. When we do that, we have a set of possible outcomes that we call 1, 2, 3, 4, 5, 6. And the probability of any particular outcome is 1 out of 6. So sort of standard uniform probability space. Okay. So let's define an event B, and I'll keep saying the number when I put things in quotes like this. I mean the number that we see when we roll the 6-sided die. So here's an event described in language. The number is odd. Now, described as a set, that means the number is 1, 3, or or 5. It's the odd things in this set. Okay? And let's say A is the event. The number is 3. So if I describe that as a set, well, that's an easy one. It's a singleton set that only contains the number 3. So without the definition, if I say I rolled the die and the number was odd, what's the probability that it was a 3? What would you tell me? Yeah. 1 in 6.
Wait, or just 4 if it's the number is 3.
Well, I roll it. I tell you it's odd.
Then that's 1 out of 3.
1 out of 3. Yeah. So the answer, we expect that the probability of A given B is 1 out of 3, but we have a definition for what probability of A given B actually means, so let's apply it and make sure it gives us the answer we expect. So that's the probability of A intersect B divided by the probability of B. We're allowed to use this definition because probability of B is bigger than 0. In fact, it's actually half in this case. So this is the probability of, well, A intersect B. So here's A, it has 3 in it, and B also has 3 in it. So A intersect B is 3, because that's the only thing in A. And B is just this set. So over on top, we have 1 out of 6, and on the bottom, we have what I would expect, right? This definition is behaving the way we would hope. You know, I roll this die, I hide it, and I look at it, and I say it's odd. What are the chances that it's a 3? Well, you kind of think, well, there's only 3 options left now, and they're all equally likely. So it should be 1 out of 3. But intuitively, that's what we think should happen. But we have to be very careful with these definitions. Because already the question about Anil's children was a little bit surprising. I mean, the answer was not something that most of you thought of immediately. Okay. All right, let's turn it around. What about the probability of B given A? Well, in words, this is me telling you, I rolled this die and it came up 3. I'm telling you it came up 3. Knowing that, what's the probability that it's odd? Should be 1, right? I mean, it's 3. 3 is an odd number, so the answer should be 1. Let's check that. So that's the probability of A intersect B divided by the probability of A. Or if you don't like that, I can say B intersect A. That doesn't make any difference. So B intersect A is 3. A is the set containing 3. So we get 1 out of 6 divided by 1 out of 6 is 1. Just like we would expect. If I tell you it's 3, it's definitely off. All right. I will just put over here the definition, the important part of the definition. let's keep testing this thing. Still working with rolling one 6-sided die. Let's say C is the event. The number is prime. So if I write that as a set, what are the prime numbers in there? Yep.
Is one prime?
1 is not prime. 2 is prime, yeah. 2, 3, and 5. So numbers other than 1 that are only divisible by themselves and 1. And the exclusion of 1 is for just to avoid a lot of you exclude it once in the definition to avoid having to exclude it all the time in every other statement about primes, basically. Okay, so this is the set C of about prime numbers that I might roll. So I can check what's the probability that I roll a 3 given that I roll a prime number. What's the answer? Yep. Should be 1 out of 3, right? Just following what we did here, just because, well, there's 2 things that make this work. The 3 comes from the fact that this is a set of size 3, so the 1/3, and it's not 0 because 3 is actually in that set. But let's, again, always be, oh, not B, this should be A given C. Probability of A and C divided by a probability of C, which is the probability of A is the set containing only 3 and C has 3 in it. So this is 3 and this is 2, 3, 5. So we get 1/6 over 3 out of 6, or 1/3. Okay. And again, let's just check probability of C given A. So I tell you that the number that I rolled is a 3. Knowing that, what's the probability that it's prime? This should be easy to check. So that's the probability of C intersect A divided by the probability of A. The top is just probability of 3. And now the bottom is also the probability of 3. 1/6 over 1/6, which is 1. So everything's behaving the way I would like it to. This seems to be the right definition for what it means to run an experiment conditional on something. And I think it also, even that technical issue that probability of B should not be 0, well, that comes because otherwise we have a problem because we're dividing by B and dividing by 0 is a problem. But even in terms of the interpretation of we run the experiment until B happens, well, if the probability of B is 0, then B never happens, so that also doesn't make sense. So that's a good, even that condition about the probability of B not being 0 is important. And one last test. Let's say B bar is the complement of B, which is that the number is even. So the even numbers there are 2, 4, and 6. And if I ask you, what's the probability that you roll a 3, given that you roll an even number? Intuitively, what's the answer? Should be 0, right? I rolled an even number. 3 is not an even number, so I can't have rolled a 3. Let's see why it's 0, where that shows up. Well, apply the definition. That's the probability of A intersect B bar divided by the probability of B bar. But now, if we look at A is the set containing only 3, and B bar is a set that doesn't contain 3, so the intersection of A and B is the empty set. So that's the probability of the empty set. Now, does anybody remember what the probability of the empty set is? If we want, we can go all the way back to the definitions. You take each element in the empty set and you add up its probability. This is an empty sum. And an empty sum, right? There's nothing in the empty set, so this is an empty sum. It has no terms at all. So it's 0. Probability of B bar is 3 out of 6. But that doesn't really matter because the result is still 0. So sometimes, like in this example, the events A and B are mutually exclusive, which means that if I tell you B happened, then A cannot have happened. And that shows up, so that means that this conditional probability will be 0. And that shows up because when you take the intersection of A and B, you get an empty set. Okay. Questions? Everybody understands? Okay. You think you understand? All right. Let's try. Back to Anil. Very slowly. We'll complicate things a little bit, or maybe not. It's hard to say. But I'm not only interested in the sexes of Anil's 2 children, I'm also interested in discussing the days of the week in which they were born. Okay? So there's some weekdays, and I'll just call them Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. So the number of weekdays is 7. And there are, there's the sexes, boy and girl. The B and G is what we're using there. So, again, Anil has 2 children. At least one of them is a boy. So our original question was, what is the probability that Anil has 2 boys? And the answer to that original question is over here. It's 1/3. So let's change the question a little bit and say Anil has 2 children. At least one of them is a boy who was born on Sunday. That's the only change. What's the probability that Anil has 2 boys? Yep.
1 out of 3.
1 out of?
3. Same as 2 boys.
That would be my guess, yep.
What's the correlation between the weekdays and the boys?
No obvious one that I can tell. I mean, this extra information doesn't seem to tell me anything new, does it? Okay, well. All right, so definitely the set S is more complicated now. The set S looks like the following. Instead of just 2 things, 2 sexes, there's actually 4 things. And I'll say that that is the sex of the first child, the day of the week that the first child was born on, the sex of the second child, and the day of the week that the second child was born on. And the sexes must be B for boy, G for girl, and the days of the week, they have to be from this set W that I wrote over there. Okay? And as usual, we're assuming everything is uniformly random. So that means that when we want to compute probabilities involving subsets of S, the size of S will always show up in the denominator. So let's get that figured out. How big is this set S? How many choices are there for the first sex? 2. How many choices for the day of week? And then 2 choices for the second sex. 7 choices for the day of week. So the size of S is 2 times 7 times 2 times 7, whatever you want to call that, 14 squared. So that's the size of S. Okay. Now we have this condition B. Says that at least one of these children is a boy that was born on Sunday. So we want to write that down as a size as a set so we can figure out its size. Well, it's easiest to do that, using divide and conquer. So at least one of them was a boy born on Sunday. So maybe it was the first one was a boy born on Sunday, and then I don't know about the second one, or maybe it was the second one and I don't know about the first one. Write that down carefully. So maybe first one was a boy born on Sunday, and then S2 D2, and that's for any gender or sex S2, and that's for any day of the week W. So that's sort of part of the possibilities. Or there was a first child born, and then a boy, second child was a boy born on Sunday. And that's for S1. And boy, girl. And D1 being a day of the week. So that's, you agree that this is the set B we're interested in, right? First one was a boy born on Sunday, and then I don't know about the second one. Or second one was a boy born on Sunday, and I don't know anything about the first one. So, I mean, ultimately we're going to be using the formula for conditional probability, which of course I erased. So on the bottom here is probability of B. And for us, that means we need to figure out the size of B. So how big is this set? Well, it's the union of two things. So I don't know, let's call this one X and this one Y. So B is X union Y, which means that the size of B is what? If I want to compute the size of a set that's the union of two sets, yep.
Wouldn't this be 14 plus 14?
Okay, so size of X is 14, size of Y is 14. Does that mean that the size of X union Y is 14? No. What are we forgetting? The intersection. So that means it's X plus Y minus the common intersection. Remember, the principle of inclusion-exclusion says if we just add up the sizes of X and Y, we'll be double counting the stuff that appears in both X and Y. We need to account for that. Okay? So for us, X, well, the first child was a boy born on a Sunday. That's all fixed. But here we still have 2 choices for the sex of this child and 7 choices for the day of the week. So there's 14 choices total. So this is 14. Y, the same situation, right? Everything about the second one is chosen for us, but we can still choose the sex of the first child and the day of the week of the first child. So that's 14. And what about this set X intersect Y? What's in there? Yep.
When there's a boy born on Sunday and a boy born on Sunday?
Yeah. So this one counts the case where there's a boy born on Sunday and another boy born on Sunday. And this one counts the case where there's a boy born on Sunday and another one born on Sunday. And that's the only thing that they have in common, right? So we need to subtract 1. So that's 28 minus 1, 27. Okay, so everything is still plausible here because 27 is divisible by 3, so there's still a chance that we're going to get the answer 1/3 that we're expecting, right? Right? In the end, our answer is going to be something like this, and I'm telling you that on the bottom I'm going to see 27 over the size of S, so the thing on top, maybe it's 9 over the size of S, in which case we get 1/3. Okay, good. Now, what's the set A? Well, that's this thing here. A is the event Anil has 2 boys. And that way I'm really interested in the question is really, what is the probability of A given B? All right, so A is, Anil has 2 boys. So let's write that down. 2 boys, that means there's a boy that was born on a particular day of the week, and another boy who was born on a particular day of the week. And that's for any 2 days of the week in W. The size of A is really easy to compute. It's 7 times 7. Unfortunately, I don't care about the size of A. That's not in the formula that I need to evaluate. And luckily for us, it's not, because 7 times 7 is 49. Then we'd be getting something like 49 divided by 27, which makes no sense. So let's figure out what it is that we want. We're interested in A intersect B. That's what we need to evaluate this formula. So what does A intersect B look like? Probably easiest if I split it up into 2 parts like I did for B. So A intersect B. So that's 2 boys, one of whom was born on a Sunday. So for example, maybe it's 2 boys. The first one was born on a Sunday, and the second one was born on any other day of the week. Or it's a boy born on some day of the week, and the second one was born on the Sunday. Okay? So that's what A intersect B looks like, right? So there has to be 2 boys, because it has to be an A, and one of them has to have been born on Sunday, because that's what it means to be in B, is that it's a boy, there was a boy born on Sunday. Okay. All right. So what's the size of this thing? What's the size of this first set in the union? Yep, 7, right? The only thing left to choose is which day of the week the second boy was born on. So that's 7. And the size of this set is also 7, because the only thing left to choose here is which day of the week the first boy was born on. So is this answer 7 plus 7? Nope, because the size of the union of 2 sets is not just the sum of their sizes, but you have to also figure out their intersection. Now, is there anything that appears in this set that also appears in this set? That same annoying case of those 2 annoying boys who were both born on Sunday, that's the only thing that can show up in both of these things, 2 boys both born on Sunday. So I have to subtract 1. Now we're done. Probability of A given B. So probability of A intersect B is, we need to know the size of A, and we have to divide by the size of S. So that's going to be probability of A intersect B divided by probability of B is equal to the size of A intersect B divided by the size of S over the size of B divided by the size of S. A intersect B is 13. B is, what did I say B was? 27. The answer is 13 over 27. Oh, that must be 1/3, right? We just need to take out. I think this is 0.4815. So 48%. Instead of 33.3%, the answer changes to 48%, 48.15%. So, anybody understand why? What's that? Yeah, if you introduce an arbitrary different factor instead of born on the day of which day of the week they were born on, it's sure, hour of the day, whatever. In fact, the more and more you tell me about this particular boy who has all of these special properties, the closer and closer the answer comes to 1/2. You can ponder that to figure out why. I don't have a good explanation that you'll hear it and say, oh, of course. That's what happens. This very more and more specific information that I give you about this boy means that actually this other child, I know it really affects less and less what happened with this other child, until the other child is basically equally likely to be a boy or a girl. If you go to the course webpage, under the notes for today, you'll see a link that shows you the set B of these 27 things, and there are stars beside the 13 of them that have both boys. But otherwise, I don't have a good explanation, other than this is the correct answer. We have to do what the definition tells us. The definition told us what conditional probability means, and it gives us the answer 13 over 27. That's it. So I think that's a good sort of jaw-dropping place to leave it for today.